So we're starting a new chapter now called electrochemistry, and this is really a topic that has a lot of applications in the real world. In this particular class, we're going to look at the theoretical underpinning of how these chemical reactions can be used to generate electricity and how to use electricity to push chemical reactions that are not spontaneous to happen. But there is multiple applications in engineering and other fields. And so I just want to mention here that one of the most common applications of this is in the design and creation of a lot of different types of batteries that you use every day. The fuel cells are used to power cars and other appliances are also an application of electrochemistry. When we extract metals from metal oxides and other mining applications, that's also an application of electrochemistry. And in fact, it also relates to biology in the sense of understanding how neurons work. Those are all based on electrical signals, which requires an understanding of electrochemistry. So there's a lot of applications there beyond just sort of the theoretical understanding of electrochemistry that we'll discuss in this chapter. Now, in order for us to understand electrochemistry, the key concept to understand first is just how electrons are passed around between chemical substances, right, between your reactants. So to do that, we're going to need to review a little bit the concept of oxidation reduction reaction or redox reaction from General Chemistry 1. So redox reactions, as you remember, are reactions where one or more reactants are transferring electrons to another reactant or reactants, right? And so there's some definitions that you need to keep in mind. One is that oxidation refers to the loss of electrons. So if reactant gives away its electron, then that reactant is oxidized. Reduction is the gaining of electrons. So for a redox reaction to happen, a reactant must give away electron, another reactant must accept that electron. So you can't just have one thing giving away, but there's nobody to accept it. So there's always have to be somebody giving away, somebody taking it. The oxidizing agent is the reactant that accepts the electrons because that reactant is allowing the other reactant to be oxidized. So it's called an agent. So in this case, it's the reactant that is reduced. And then the reducing agent, on the other hand, is the reactant that is oxidized because it allows the other reactant to be reduced. Okay. If you look at a simple example of a redox reaction here, which is a reaction between sodium and chlorine gas to produce sodium chloride, if you look at the periodic table, you see that sodium has 11 electrons in the atom state. A chlorine gas, each one of the chlorine has 17 electrons. And in the sodium chloride, the sodium, of course, here is an ion, it's a cation, so there's a +1 cation. And in that case, that means that it's lost one electron. So going from here to here, the sodium has been oxidized. The chlorine, on the other hand, has turned into a chloride ion, which has 18 electrons. So going from 17 to 18, that means it's gained one electron. So the chlorine element has now been reduced. Okay, so that one is a little typo there. I should say reduced. And so that's a simple example of a oxidation reduction reaction and seeing how electrons are being transferred from one reactant to another. A lot of times we don't actually count electrons like the way that I just showed you from the atom going to an ion or some other ways. The reason is because it's not always possible to do that. So if you're dealing with something like a covalent compound, say for example CH4, it's really impossible to tell, what is the change in the number of electrons from, let's say, carbon in its element originally all the way to the compound form, which is the methane form here. So what we do is we use this technique or tool called oxidation states, or sometimes also called oxidation number. And that's just a simple way for us to count electrons to help us determine what is the change of the electron going from reactant to product. And there's a certain set of rules here to follow in terms of determining oxidation state. I'm not going to necessarily go through this. This is actually something that should be discussed before in General Chemistry 1. But what I'll do is apply a couple of examples. I will just mention that the key ideas here that you need to keep in mind is a lot of the beginning rules are very similar to the rules for determining ionic charges, right? So all the group 1, for example, will have +1, all the group 7 would have -1, and so on. But the nonmetals part here is really what matters a lot. So I would ask you to focus on this last bit of the rules, which is that you have to follow this in sequential order. So F is always -1. This is in oxidation number term. Oxygen is -2, except when you're dealing with peroxide, where oxygen is -1, and then hydrogen is +1, except when you're dealing with hydride. In hydride, hydrogen is -1, and hydrides are compounds where hydrogen is bonded to a metal. And then afterwards, you follow the rest of these other rules, which is that 7 is -1, group 6 is -2, group 5 is -3. These are all not guaranteed, but they're typically that. So what you have to do is actually determine it. So you follow this order sequentially for the nonmetals. For the metals and for sort of compounds, you can follow the rules that you already know from ionic compounds. So let's actually do some problems here to help us determine this, right? So let's take a look at this. We have Al2O3. So when we have something like that, we can just, remember that aluminum is in group 3. So that's going to have a charge of +3. Oxygen, as we said earlier, is always -2, except when it's dealing with peroxide. This is not a peroxide, so oxygen is -2 in this case, okay? And the sum of the two, when you add it together, should add up to 0. So you get -6 with the 3 oxygens and +6 with the 2 aluminum, so you indeed get 0 total. KMnO4 may be a little harder, but let's take a look at it. Here we have a group 1 cation, so that's a +1. A lot of times with this polyatomic ion, you might remember from manganate, is a polyatomic ion, MnO4 minus. You can just separate it out if it's an ionic compound and take a look at that polyatomic ion on its own. So we're talking about this species where the total has to be -1. The oxygen and the manganese, we have to decide which one we want to determine first. Well, manganese is a multi-charge cations, as you might remember from nomenclature discussion. So the oxygen here is what we can tell. It has to be -2, so I'm going to put a -2 over the top here. And so that one is -8. And so therefore, the manganese, in order to add up to -1, has to be +7, okay? And so that's why those three are the oxidation states for those 3 elements there. Let's take a look at the third one. This is sodium hydride. So again, hydrogen, as I said earlier, is always +1, except when it's being combined with a metal, which is this hydride form. So now we know that sodium is a group 1 cation, so it's going to be +1. The hydrogen has to be -1 in order to get the total to be 0. So that's why it's +1 -1 there. The last one here I want to ask to consider something that students often get confused about. So that's Fe3O4. Here again, Fe has multiple charges, so I'm going to assign the oxygen first, and oxygen is -2, right? So that gives me -8 here since I have 4 oxygens. So therefore, the 3 iron must add up to +8. And so the only way that would work is if each iron has a +8/3 oxidation state. And so this is where that whole idea about oxidation state, which is that it's just a fictional charge that we assign to these elements to help us count, whether the electrons are lost or gained. That's when that's really how you see that it's just a fictional charge, right? So the iron is not going to have a charge of +8/3. It's going to have a charge of either 2 or 3, right? But again, this is not an actual charge. It's just a number that we use to help us determine whether something is oxidized or reduced. Now, how do we actually use that to determine whether something is oxidized or reduced? Well, we look at the change in oxidation state. So if the oxidation state increases, so it becomes more positive, right, or less negative, either way, then that's what we refer to as oxidation. So again, if the oxidation number goes from 2 to 3, for example, or -2 to -1, right? In both cases, we're increasing our oxidation number, so that's oxidation. And of course, the idea behind that is that electrons are negatively charged, so if you're losing electron, which means you're oxidized, then your oxidation state should become more positive or less negative, right? Reduction is then the opposite. If an element is reduced, that means this oxidation state is going to decrease, right? It's going to go less positive or more negative, okay? And so the key for determining whether something is oxidized or reduced is always to assign all the oxidation states first, and then afterwards seeing what kind of change occurs for specific elements.